Since the beginning of this semester, we've been studying algebras that were defined with only a single operation. We've gotten a lot of mileage out of that, particularly with the study of groups. But since you were relatively young, you've been exposed to structures that have had multiple operations. In particular, I think probably the most popular one, the one you're the most familiar with, is the set of real numbers. Well, you've looked at several operations on the real numbers: addition, multiplication, subtraction, division. But in a sense, division is just an inverse of multiplication. Subtraction is just an inverse of addition. So we really don't lose anything by studying the real numbers with just the two properties of addition and multiplication. They satisfy many of the properties that we have looked at throughout the semester, and ones that you've become very familiar with since you were in grade school. I want to look at some of those properties right now, some of the axioms that the real numbers satisfy under addition and under multiplication. What you're looking at here is the first page that I typically hand out whenever I'm teaching a course in real analysis, a course that studies the real numbers. Some of you have already taken this course. Some of you will be taking this course soon. In any case, all I'm really interested in here is looking at the axioms that the real numbers satisfy under the two operations of addition and multiplication. These first four axioms talk about the properties that are satisfied under addition. This first one says that addition is associative. The second one says addition is commutative. The third one says that the real numbers have an identity element under addition. We usually refer to that as the number 0. And then the fourth one says that every real number has an additive inverse. And so if I put these four axioms together in the context that we've been studying for this whole semester up to this point, these four axioms say that the real numbers under addition form an abelian group. Great. We know lots about abelian groups. So already we know lots about the real numbers under addition. Let's look at the multiplicative axioms. This first one says that, well, it says multiplication is associative. It says multiplication is commutative. It says that there's an identity element in the real numbers under the operation of multiplication. And this fourth one has a little proviso here. What it says is that if I have a non-zero element, then there's always a multiplicative inverse for that element. Of course, we have to throw 0 away whenever we're considering multiplicative inverses because, well, 0 times any number is equal to 0, so you're never going to have 0 multiplied by some multiplicative inverse that gives you 1. So that's impossible. So we have to throw that out, but it's a minor compromise. And so these four together say that the set of real numbers minus 0 are, well, let's see, associative, commutative, have an identity element, and have multiplicative inverses. So the real numbers without the element 0, that forms an abelian group. So we know lots about that as well. And then we have this ninth axiom down here that it tells us how multiplication and addition interact, right? And we usually refer to this as the distributive property, right? We say that multiplication distributes over addition. And really we should have this written in two forms, this one as well as b plus c times A equals B times A plus C times A. We'll talk about that in just a moment. So the real numbers under addition form an abelian group. The real numbers without zero under multiplication form an abelian group. And the distributive property tells us how addition and multiplication interact with one another. An algebraic structure with two operations that behave in that manner in which we've just seen that the real numbers behave is referred to as a field. It's a very rich algebraic structure in which we can prove many, many theorems, and eventually we will. For now, let's look at the definition of a field written out on the whiteboard. So here it is. A field is a set, I'll call it F, together with an operation that we refer to as addition and an operation that we refer to as multiplication that satisfies the following properties. F under addition is an abelian group. F without the additive identity element is an abelian group. And multiplication distributes over addition. We're going to denote this algebraic structure as a triple, similarly to the way we wrote our notation for groups, right? We wrote our notation for groups by putting the set name and then the operation. But we have two operations this time, and we will always refer to the first operation that is listed as the additive operation and the second one as the multiplicative operation. So I've got some examples here of a lot of familiar sets, ones that you already have a notion of both addition and multiplication on. Right? We can talk about, for instance, Z3 together with addition mod 3 and multiplication mod 3. Similarly, Z4 and Z5. Q is the set of rational numbers, right? E, I'm going to refer to as the set of even numbers, even integers. Z is the set of all integers. I'm going to use this notation, 5Z, to mean all multiples of 5. Similarly, I could call E, for instance, 2Z, right? All multiples of 2. So that would be another way of indicating E. But I could also talk about 3Z or 17Z, what have you. By this notation, I'm indicating the set of all 2 by 2 matrices with real number entries, right? So be a 2 by 2 matrix, and each of the 4 entries is a real number. Similarly here, this is the set of all 2 by 2 matrices. This time, all of the entries are coming from Z2. So all of the entries are either 0 or 1. What I'd like you to do is pause the video for just a moment and give yourself some time to see if you can decide which of these familiar sets, together with the usual operations of addition and multiplication that we intend whenever we're talking about those. So here it would be addition mod 5, multiplication mod 5. Here it would be a usual matrix addition and that strange matrix multiplication that we apply to matrices, would be what I mean there. So with the usual operations that we associate with these sets of addition and multiplication, see if you can decide which of them satisfy all of the axioms for being a field, which of them form abelian groups under addition and also abelian groups under multiplication when we take away the 0 element, and which ones distribute over addition. Pause the video for just a moment and think about that. Okay, so what did you decide? Well, it turns out that very few of these turn out to be fields. Actually, only a very small handful of them. Right? Of these algebraic structures, the only ones that are fields turn out to be Z3, Z5, and the rational numbers. What's wrong with the rest? What keeps the other ones from being fields? Well, the even integers, for example, have no multiplicative identity, right? If it did have a multiplicative identity, it would be 1, but 1 isn't even. So that doesn't even satisfy the identity property. 5z has the same problem. The multiples of 5 do not include the number 1, right? 1 would have been the multiplicative identity if it were there, but it's not, right? So those two fail for that reason. Z4, Z, right, the integers, the matrices with real number entries, the 2 by 2 matrices with entries in Z2, well, they do all have multiplicative identities, but each of them contain elements that fail to have a multiplicative inverse. For example, in Z4, there's nothing you can multiply by 2, for example, that's going to give you the identity. Of course, the identity in Z4 is 1. But 2 times 0, 2 times 1, 2 times 3, none of those give us the identity element. So 2 does not have a multiplicative inverse. Z has the same basic problem, right? No multiplicative inverses. Why? Well, look at 2 here. The multiplicative inverse in Z, let's see. So this is usual multiplication. I would have to multiply by a half in order to get me the identity element 1, but 1/2 is not an integer. So 2, for example, has no multiplicative inverse. In fact, the only elements that have multiplicative inverses in Z are 1 and -1, both of which are their own inverses, right? 1 is the inverse of 1, -1 is the inverse of -1. No other integer has a multiplicative inverse. I will leave it to you to find elements in our collection of matrices that don't have multiplicative inverses. In addition, multiplication is not commutative for matrices, and it's easy to find counterexamples to show that fact, right? So there are plenty of reasons for these other structures, the ones other than Z3, Z5, and Q, to fail to be fields. However, it does happen to be true that every one of these structures, right, every one of the structures that you looked at, here they are again, every one of these structures are abelian groups with respect to addition. Every one of them. All of these structures also satisfy the distributive property. And in addition, under multiplication, the associative property holds as well. So they do fail to be fields for the reasons given up here, but they do all satisfy some of the properties of a field. What we'd like to do is to develop a set of axioms that applies to all of these structures. After all, they are all important structures to us, right? Those are all very natural structures to study, and we don't want to just get rid of them simply because they're not all fields. We'd like to be able to study them together so that we can efficiently prove theorems about all of them simultaneously. This actually is the power of using an axiomatic system. in order to study mathematics, right? By concentrating on the properties, concentrating on the axioms that structures satisfy, by proving things that satisfy these properties, we're actually proving results about many, many algebraic structures all at the same time, right? So long as we know that an algebraic structure satisfies a particular set of properties, so long as we've proven something to be true whenever a structure has those properties, then we've proven it for all of those examples simultaneously. Well, by studying the ones that we've just looked at, it seems that a reasonable set of axioms to focus on would be that the structure under addition be an abelian group. Remember, all of those examples were abelian groups under addition. All of the examples that we looked at were associative, right? They all satisfied the associative property with respect to multiplication, and they all satisfied the distributive property, right? And again, by this I mean that A dot B plus C is A times B plus A times C, but also in the other direction, right? Here I'm not assuming that the structure is commutative with respect to multiplication. So I'm going to have to go in the other direction as well if I want the property of distribution to fully hold. And so B plus C times A, I want that to be B times A plus C times A. So any structure that satisfies these three axioms, we're going to call a ring. So anything that we can prove about a ring, we have proven about all of these and many other structures all at the same time. We don't have to individually prove something about each one. We know that they all satisfy these properties of a ring. So by focusing on the properties and proving things about structures that satisfy those properties are proving results about many, many structures at the same time. So before we go on, I'd like to adopt a couple of notation for identity and inverse elements, so I don't have to keep on in every proof saying, let's let this represent the identity element and so on. So here we go. Most of these are going to look familiar. So whenever I'm looking at the ring with respect to addition only, if it has an identity, oh, it does, yes, under addition, it always has an identity element. 0 is a reasonable thing to use for that. That's what we commonly, after all, if I talk about the additive identity in the real numbers, that's the symbol I use. And so often that's the symbol that's simply adopted no matter what structure we're looking at, if we are considering the additive operation on that set. But sometimes I like to use Z as well, so that, well, frankly, so that the statement doesn't look too obvious. We're so used to the symbol 0 that if I said something like A times 0 equals 0, well, that sounds more obvious than saying A times Z equals Z. Looks like we're actually proving something that might have a little bit more substance. Has the same amount of substance, of course, regardless of the symbol used, but sometimes it's just a little bit more satisfying to use the symbol Z instead. Identity element under multiplication, again, because 1 is the symbol that we use for the real numbers. That's often the symbol that's adopted. We're really more used to using the symbol E in this course. And so I will often use E instead of 1, but I'll interchange them. Doesn't really matter. Inverses, we've usually been using this notation for inverses, and this is what I'm going to use specifically for additive inverses. Sometimes I use the more common opposite of notation. But then if I'm talking about the inverse element of with respect to the multiplicative operation, I'm going to use the common x to the -1 as representing the inverse element. Okay, so with all that in mind, let's talk about some theorems that are true for all rings, right? So any structure that satisfies those three properties that we identified as defining a ring will satisfy these theorems as well. So let's let R be a ring, and let's let A and B be members of R. So the first thing that turns out to be true for all rings is that anytime you multiply by 0, you get 0. Notice how it actually looks like whenever I use the symbol Z, that it looks like it says a little bit more, doesn't it? But that's exactly what it does say. Whenever I multiply by 0, I get 0. And this is interesting too, because think about it. Z is the additive inverse of R, the additive inverse of our ring. And this is a statement about multiplication. So in a sense, this is combining, this is a statement that combines the notions of the additive and multiplicative identity, or the additive and multiplicative operations on R. And similarly, we have Z times A being Z. I kind of need to write those separately because, again, we're not assuming that multiplication is commutative. Another theorem that happens to be true is that if I take A and multiply it by the additive inverse of an element, I get the additive inverse of the product. Well, this is what you've known since grade school as when you multiply by a negative, you get a negative. But it looks more substantive, I think, whenever it's written in this notation. Again, it's a statement that combines the notions of multiplication and addition in as much as this is the additive inverse that we're multiplying by. And finally, if I multiply the additive inverses of two numbers, I get the product of those two numbers again. This is what you've known since grade school as when you multiply two negatives, you get a positive. It's not exactly what it says, because after all, these could have been, A could have been a negative number, and so A inverse would have been positive. But it captures that idea of multiplying two negatives gives you a positive. And again, it's combining the notions of addition and multiplication in as much as I'm multiplying additive inverses. So the proofs of these are homework. I'd like you to see if you can do those yourself. I will also do them. We'll compare answers. And so that's what I'm asking you to do for next time. All right, so those are some theorems that are true for all rings. And now I'd like to look at some properties that you might expect to be true for rings, but which actually fail. So first one. So you're used to the fact that if you multiply two real numbers together and get 0, one of those two numbers had to be 0. Turns out this is not the case for some rings. It's true for the reals. The reals are an example of a ring, so sometimes it's true. But there are counterexamples, and you can find counterexamples in Z4, for example. You can find counterexamples in 2x2 matrices with entries in Z2. You can also find them with entries in R, but there are fewer to pick through here, so maybe a little easier to find some. Another property that you might expect to be true is that if you multiply two numbers by the same thing, so if I take A times B and A times C and I get the same thing, then you're used to saying, oh, well, let's just cancel the A's. Of course, we're assuming here that a is a non-zero number. If a were 0, then, well, of course, we're assuming here that a is a non-zero number. This turns out to have counterexamples as well, also in the same rings. And we'll see toward the end of this video why we're able to look in the same places for counterexamples to both of these properties. So let me give you some examples, some counterexamples. So in Z4, we'll just look at this first one. 2 times 2 is equal to 0, right? 2 times 4 is 4 in the integers, but 4 is equal to 0 in mod 4 arithmetic, right? But 2 isn't 0, so I have two non-zero numbers being multiplied together and giving me 0, right? Happens here, doesn't happen in the reals, right? And similarly, let's see, 2 times 1, so 2 is a non-zero number, but 2 times 1 and 2 times 3, well, they both equal 2, don't they? 2 times 1 is 2, 2 times 3 is, well, 6 in the integers, but 6 is equivalent to 2 in Z4. So I have, A times B equals A times C, but A and C are different. Or I'm sorry, B and C are different. In Z2, well, let's see. Here are two non-zero matrices, which if I multiply them together, I get the 0 matrix, right? Neither one of these are 0. So that's a counterexample to statement 1 up here. And similarly, if I took this matrix and multiplied it by that one and then multiplied it by that one, go ahead and check it out. You'll see that you get exactly the same thing. In fact, I believe you get 0 both times. But these two are not identical, right? So that would be a counterexample to number 2. Some terminology. Certainly you're familiar with this first bit, right? Because 3 times 4 is equal to 12, and we're looking at the integers right now, multiplication in the integers. We call 3 and 4 both divisors of 12, right? That's old hat. You know that. But it's a little funny to talk about this because I'm looking in Z6 right now. In Z6, 2 times 3 is 0. And so for the same reason I'm calling 3 and 4 divisors of 12 up here, I'm going to call 2 and 3 divisors of 0 here. Sounds funny because ever since elementary school, you've been taught never divide by 0. You can't divide by 0. Well, actually, you can in some other structures. And here we have such a thing, right? 2 times 3 is 0 means that 2 and 3 are divisors of 0. Sometimes we also will refer to them as 0 divisors. Also, let's just go ahead and state that formally. So if A and B are non-zero elements of a ring for which A times B is 0, we call A and B 0 divisors of R. Another definition. So let's start with a ring. And let's say that we're in a ring that does satisfy this property that we're familiar with, that does allow us to cancel. So if A times B equals A times C, always implies that B is equal to C. And of course, I'm assuming A is non-zero here because otherwise I'm just multiplying by 0. And we've already shown, actually we've said you will show in homework that always gives you 0. So if we have this equality implying this equality for non-zero A's, then we're going to say that R has the cancellation property, right? So it allows us to cancel whenever we have A times B and A times C equaling the same thing, A being non-zero. Okay, so it turns out that this notion of the cancellation property and this notion of zero divisors are related very, very strongly. Turns out that if a ring has the cancellation property, then it doesn't ever have zero divisors. And the other direction is true as well, right? If R has no zero divisors, it turns out that R has the cancellation property. And so we'd like to prove to you that this is the case. We're going to start by assuming that R has the cancellation property and prove that it has no zero divisors. So let's see. So we're assuming R has the cancellation property. If we're going to prove that R has no zero divisors, then we're going to have to probably start with two elements that equal whose product is zero. And that's exactly what we have here. And so let A and B be members of the ring whose product is zero. Well, if we're going to show that R has no zero divisors, what we're going to have to show is that either A is zero or B is zero, one of those two. So let's see if we can do that. We're going to do this in two cases. The first case is going to be especially easy. So let's see, case one. Suppose A is zero. Well, then our conclusion is true, isn't it? It's true that either A is zero or B is zero, if we're supposing that A is zero. That's case one. We have to go through all possible cases. We want to be exhaustive with our cases. So let's see. If I'm going to be completely exhaustive and one of my cases is A equals zero, then I guess the other possibility is that A isn't zero. Certainly it's either zero or it's not. And so if I can prove in both of those cases that my conclusion is satisfied, then I will have done what I set out to do. Again, case one supposes A is zero. Obviously, my conclusion is true. Second case, let's suppose A isn't zero. Well, if I'm going to show that my conclusion is true, then I'm going to have to somehow prove that B is equal to zero. And that's what I'm going to try to do. Now, since we're assuming that A times B is zero, and since you're going to show for homework that A times zero is zero, that says that A times B and A times zero are equal to each other. Right? But A is non-zero, and we're assuming that we have the cancellation property. So I can cancel my A's, and whenever I do, what I wind up with is that B is zero. And so again, my conclusion is true. Either A is zero or B is zero. In this case, my conclusion is true because B is zero. So whether A is zero or A is not zero, I wind up with my conclusion being true. And so I have shown that, that R has no zero divisors. Now let's go in the other direction. We're going to assume that R has no zero divisors and prove that our ring has to have the cancellation property. All right, so here we go. Suppose that R has no zero divisors. And if we're going to prove that R has the cancellation property, then we're going to have to start with a non-zero element and find two elements B and C for which A times B is equal to A times C. So that's our setup. We want to prove now that B and C are the same element. That's what we are going to need to do in order to show that R has the cancellation property. Well, let's see what we've got. So we're assuming this. We're assuming A times B is equal to A times C. And that means that I can add the additive inverse of A times C to both sides. Remember, we're in a ring. A ring with respect to addition is an abelian group, so we have an additive inverse of A times C. Of course, whenever I do that on the right, I'm just going to get the zero element, right, the additive identity, because I added the additive inverse to A times C. Over on the other side, I'm going to get, let's see, this probably is a little bit clearer if I maybe put parentheses around those two elements. And so what did I use here? Another one of the properties that you're going to prove for homework, that whenever you think of it as multiplying by a negative, you get a negative. But now I'm in a position where I can use the distributive property, kind of in reverse, right? A distributes over addition, and this is the result I get whenever I have my A times B plus C inverse, additive inverse. So what do I have? Why does this help me? Well, by now we might have forgotten what we're trying to do. We're trying to show that we have the cancellation property, which means we're trying to show that B and C are the same, and we're assuming that R has no zero divisors. A was a non-zero element. And so if we have no zero divisors, since A isn't zero, B plus C inverse is going to have to be. If it weren't, right, if this were non-zero, since this is non-zero, then I would have had zero divisors, right? I'm assuming I don't have any. So what I've just shown is that B plus C inverse, that's going to have to be zero, right? Again, since A is non-zero and R has no zero divisors. Well, let's just take that equation, add C to both sides, use the associative property, and what I have now is that B is equal to C. That's exactly what I was trying to show. So if A is a non-zero element that satisfies this equation, then we have this equation satisfied as well. And that shows that R has the cancellation property whenever R has no zero divisors. And that is our introduction to algebraic structures that have multiple operations. In particular, we've talked about fields, that very rich structure for which multiplication without the additive identity element was an abelian group, and the set with respect to the additive operation was an abelian group, and that the distributive property tied those two operations together. So we looked at that. And then this weaker structure, one that had fewer properties and therefore allowed more examples to be to satisfy those properties, we called that a ring. I look forward to discussing algebraic structures with multiple operations further, and we will continue that in our next video. Until then, take care, and I'll see you then.